All right, in section 2.3, we are covering applications of the derivative. So what you're going to see here is a whole bunch of vocabulary, which should be review for the most part, but it's a good idea to kind of read through these. We talk about cost, fixed cost, total value cost, just total cost, or sometimes that's just called cost. Marginal cost. Now that one is probably a new one, or it might be a new one to you, or you might have heard of it before. It's the cost of producing the next item. Companies sometimes want to know, okay, we know the cost of however many we're making now, but what if we wanted to do just one more item? How much would that cost? And then we have demand, revenue, total revenue, and then marginal revenue is similar to marginal cost in that it's going to be the revenue gain from producing one more item. So there's a mistake here. It's the revenue. From producing the next item. Sorry about that. So there's a linear way to represent marginal revenue or marginal cost. You can just take the cost of the next item and subtract it from however many items you have, the cost of however many items you have, and then you have cost for that next item. But typically it is easier to find it using the derivative. So just go through those vocabulary words as you need to, and we'll look at some examples. So this one says, suppose a product's revenue function is given by R of Q equals negative 6Q squared minus 300Q. We want to find an expression for the marginal revenue function and simplify it. So here all we're asked to do is find R prime of Q, which is negative 12Q minus 300. And from that function, we could find the marginal revenue at any Q. Part B, the cost of producing X units of stuffed alligator toys is C of X equals 0.001 X squared plus 6X plus 5,000. Find the marginal cost at the production level of 1,000 units. So again, we want to start by finding C prime of X, which is going to be 0.002 X plus 6. And at 1,000 units, we just need to plug 1,000 in for X, and we get 0.002 times 1,000 plus 6. Well, 1,000 times 0.002 is just 2, and 2 plus 6 is 8. So that'll be the marginal cost at 1,000 units. Part C, the total cost in dollars to produce Q units of a good is given by the function C of Q equals 5.1 Q plus 52,000. What is the total cost to produce Q equals 8,200 units? That's just a matter of plugging in 8,200 into the function. It's not asking for marginal, it's asking for total, and that total cost function is what's given. So 5.1 times 8,200 plus 52,000. And if we do our arithmetic correctly there, we should get 93,820. Is going to be the cost to produce that many units. What is the cost to produce the 8,201st item? So in other words, the next, that screams marginal cost. So to get marginal cost, we need the derivative of the cost function, which is just 5.1. So it's a constant function. So no matter what we plug in it, we're going to get 5.1. So the answer for this is just 5.1. Suppose your demand function is given by d of q equals negative q squared minus 2q plus 512, where q is in thousands of units sold and d of q is in dollars per unit. If 20,000 units are to be sold, what price should be charged for the item? Okay, so it's in thousands of units, so our value is really just 20. Because 20 times 1,000 is 20,000. So we're just trying to find what we get when we plug 20 in. So basically d of 20. So it's going to be negative 20 squared minus 2 times 20 and plus 512. And when you do that, you get 72. So it should be $72 should be charged. If a price of $257 is set for this time, how many units, or for this, not time, but item, how many units can you expect to sell? Give your answer as whole units, not in thousands of units. This one, we're going to take our demand function and we're going to set it equal to the price that we want and solve for Q to get how many units. So you just need to subtract 257 from both sides since it's a quadratic function, and you get negative Q squared minus 2Q and plus 255 equals 0. So it's a quadratic function, and you can use your quadratic formula to solve it, and you're going to get that Q is 15. So 15 units. At what value of Q does d of Q cross the Q axis? That's just asking us to take the d of q function, set it equal to 0 and solve. Again, you can use the quadratic function or formula, and you should get that q is 21.65. Now you might get two answers and one of them's a negative, but it doesn't make sense to have negative items, so we throw out that answer. E, let the demand function for a product be given by the function d of q equals negative 1.35q plus 290, where q is the quantity of items in demand and d of q is the price per item in dollars that can be charged when q units are sold. Suppose fixed costs of production for this item are $5,000 and variable costs are $8 per item produced. If 51 items are produced and sold, find the following. We want the total revenue from selling 51 items to the nearest penny. Alright, so remember that if you go back to the beginning of your definitions, revenue is equal to price times quantity. And the quantity of items sold is given as d of q, and or the demand function, and then the price okay, so that is going to be d of 51, because demand and price are often thought of as the same thing, and quantity is 51. So we have to plug 51 into the d of q equation, which is going to be negative 1.35 times 51 plus 290. So that whole quantity is multiplied by 51. And if we do that correctly, we should come up with 11,278.65. Alright, we want to find the total cost to produce 51 items. So they tell us that the fixed costs for each item are $5,000 or for this item, and the variable costs are $8 per item. So it's going to be 8 times 51 plus 5,000. And that's going to be 5408, 5,408. Alright, and last we want profits. So profit is equal to revenue minus cost. Well, we found revenue in one. That was 11,278.65. We found the cost in the second one, 5,408. If you subtract those, you should get 5,870.65. Alright, F. A baseball team plays in a stadium that holds 64,000 spectators. With the ticket price at $9, the average attendance has been 29,000. When the price dropped to $5, the average attendance rose to 32,000. So find a demand function D of Q, where Q is the quantity / number of spectators. We're going to assume that D of Q is linear. So essentially what we've been given are two coordinates, and the demand function, or the price, so D of Q is going to be your price and Q is the quantity or the number of spectators. So we want to write our two coordinates as according to who is the independent variable and who's the dependent. So the number of spectators is your independent and the price is dependent. So you get your 2 points. Oops, I did that wrong. Sorry. Not 64,000. It was 29,000 for $9. And the other coordinate is 32,000 for $5. So we find M. M is going to be 5 minus 9 over 32,000 minus 29,000. Well, that's equal to -4 over 3,000, which reduces to -1 over 750. To get B, we take either one of these points. I'll take the first one, and it's going to be 9 is equal to -1 over 750 times 29,000 plus B. And if we solve that correctly, we get that B is 143 over 3. I'll trust you to do the algebra there. So we finally get our function. It's going to be -1 over 750 Q plus 143 over 4. Alright, in applications, the derivative will represent rate of change at a specific point. Some other examples of this would be speed, something spilling, or a disease outbreak. We'll see more of these types of problems in the upcoming section.